Welcome back. In our previous video, we explored the California housing dataset and prepared our data for modeling. Now we'll implement our linear regression model to predict house prices, evaluate its performance, and then interpret the results in a real-world context. So first, we're going to prepare our data for modeling. We'll split the data into training and testing sets, with 80% for training and 20% for testing. So we're also scaling our features using the StandardScaler. While scaling isn't strictly necessary for linear regression, it can help with interpretation when features are on different scales. Now we'll visualize our linear regression model and fit it into our training data. This process calculates the optimal coefficients that maximize the error between predicted and actual values. Let's initialize and fit the model with our code. After fitting the model, we'll make predictions on our test data and then evaluate its performance. We'll calculate metrics like root mean squared error, RMSE, and the R-squared, which are found in the Scikit-learn metrics module. We'll evaluate the model, and then print, and then display our coefficients. So let's take a look at the output. So it looks like our model achieved an RMSE of about 0.73. which means our predictions are off by approximately $73,000 on average. The R-squared value of around 0.60 indicates that our model explains about 60% of the variance in house prices, which is a decent result. Now let's take a look at the output showing our model coefficients. So the coefficients tell us how much the target variable changes with a 1-unit change in each feature, holding other features constant. So for example, a 1-unit increase in median income, MEDINC, is associated with about 0.83 increase in median house value, equivalent to $83,000, which is pretty substantial. And negative coefficients, like the one for average occupancy, suggest that as occupancy increases, house values tend to decrease, potentially indicating overcrowding. So now let's visualize our model. To do that, we'll create a simple regression line for the most impactful feature, median income against our target. Since our full model uses multiple features, we're creating a separate single feature model just for this visualization. We'll extract MEDINC from the test data. We'll create a simple linear regression model for MEDINC alone for visualization. And then we'll plot scatter and regression line. Now let's take a look at the results. So this plot shows the actual house values against median income with our regression line in red. While there is a clear upward trend with the line sloping from bottom left to top right, you can also see quite a bit of scatter around the line, with many dots appearing both above and below the prediction line. This scatter explains why our R-squared isn't closer to 1.0. Many other factors besides income affect house prices. Now let's analyze the residuals, the difference between actual and predicted values. To check our model's performance more thoroughly, we'll create 3 plots here: a scatter plot, a histogram, and a QQ plot. We'll calculate residuals, we'll add the plot code, and now we'll draw a histogram of residuals, and now the code for the QQ plot. Let's take a look at the results. The residuals versus predicted values plot helps us assess our model fit. Looking at this plot, we can see that the dots don't form a completely random scatter. There is a visible curved pattern where the residuals are more negative for middle range predictions and more positive for both low and high predictions. This curved pattern suggests our model might be missing some nonlinear relationships in the data. So the histogram of residuals shows their distribution, with the residual values on the x-axis and their frequency on the y-axis. And our distribution has a center peak near 0. This indicates our model tends to underpredict more than overpredict. Now we're taking a look at our QQ plot, which compares our residuals to the theoretical normal distribution. Looking at this plot, the residuals follow the diagonal reference line fairly well in the middle section, but deviate significantly at both the lower level and the upper right end. This S-shaped pattern indicates our residuals have heavier tails than a normal distribution, confirming what we saw in the histogram. Now let's interpret our results. The RMSE of 0.73 tells us our predictions have an average error of about 73,000. The R-squared of 0.60 indicates our model explains 60% of the variance in house prices. The coefficients show us that the median income has the strongest positive impact on house prices, while higher average occupancy tends to lower house prices. The latitude and longitude coefficients suggest that location significantly affects housing values in California. Our residual analysis shows that while our model performs reasonably well, there might be some nonlinear relationships that it's not capturing. This is common in real world data and could be addressed with more advanced techniques like polynomial features or other algorithms. In this demo, we saw how linear regression helps us understand relationships between features and then make predictions. Thanks for joining. Now let's keep building.